Hello, you're listening to the Science of Everything podcast, episode 98, Electromagnetic Radiation. I'm your host, James Fodor. So, in this episode we are going to pick up from where we left off way back in episode 61 on magnetism, which in turn follows on from episode 57, Electric Current and Circuits. So I strongly recommend that you listen to both of those prior to listening to this one, because I'm going to assume a modest amount of knowledge. I'm not going to go over and explain all the details of electric charge and magnets and so forth. I'm going to assume you have a basic knowledge of that. And what I'm going to talk about in this episode is how the interaction between the electric and magnetic fields gives rise to electromagnetic radiation and the various phenomena that arise as a result of that, in particular the electromagnetic spectrum, radio and TV. I'll talk a bit about the speed of light, I'll talk about radiation and antennae, and I'll also, at the end, just for a bit of extra interest, I've thrown in some discussion about microwave ovens and a bit of discussion about how they work. Also, before we jump in, I want to apologize for the length of time since the previous episode. It's been quite a few months now, and I feel bad about that. I've been wanting to get this episode out for a while. I've had a number of personal issues lately that have been taking up my time to deal with, essentially. I've been experiencing a fair bit of depression, and that's not conducive to, maximal productivity with respect to podcast episodes. So I think things are a bit better now, so that's on a positive trajectory, which is nice. But at any rate, I do apologize for that, and I'm hoping that there'll be a increased frequency of episode production in going forward. Okay, so I've already told you about the recommended prerequisites, so let's just jump straight in and introduce the concept of electromagnetic waves. So, during the study of electric and magnetic fields back in the 19th century, Maxwell, who put together the four famous Maxwell's equations, which I talked about in episode 61, he realized that there was a fundamental symmetry between electric fields and magnetic fields. And on the basis of the different equations, he determined that a change in an electric field produced a magnetic field, whereas a change in a magnetic field produced an electric field. So there's a direct correspondence between one or the other. When one changes, the other is produced. Now, this relationship is critical because it means that you can have a self-sustaining, propagating what's called an electromagnetic field, even in empty space. I mean, we know that we can have an electric field if you have electric charge that is clustered in a particular area, or if you have a magnetic dipole or a bunch of magnetic dipoles in a particular area. You can have magnets, you can have electrical charge. The key thing here is, though, that electromagnetic radiation, or electromagnetic waves, I'll kind of use those terms interchangeably, can exist even in the absence of any charges or magnetic dipoles. Simply because if you imagine starting off with a changing and oscillating electric field, the rate of change of that field will then be proportional to the magnitude of the magnetic field. Conversely, the rate of change of the magnetic field will be proportional to the magnitude of the electric field. This is all given by Maxwell's equations. So the point is that Maxwell's equations, if you just sort of draw out this logical conclusion of them, predict that there will be these things, which we'll call electromagnetic waves, which can exist even in a vacuum, even in the absence of any material there, these self-propagating, self-sustaining waves that can exist. And it further predicts, these equations further predict the speed at which these electromagnetic waves will travel through a vacuum. And it turns out that the speed of these is equal to the 1 over the square root of two numbers that are part of Maxwell's equations. These numbers are called the electric constant and the magnetic constant, epsilon naught and mu naught, if you've seen the symbols. The point is that these are just numbers that appear in Maxwell's equations, and they basically determine the permittivity or permeability, it's called, of the vacuum to magnetic and electric fields. So basically they describe how easy it is to generate an electric field in the vacuum or a magnetic field in the vacuum, respectively. So what Maxwell worked out is that his equations predicted that there would be these self-propagating waves that could exist even in a vacuum and would travel at this particular speed, which was equal to 1 over the square root of epsilon naught times mu naught, right? Now, it just so happens that this is exactly equal to the speed of light in a vacuum, which we conventionally call c. So this was quite a remarkable discovery, because we're like, well, hang on, we predicted that these waves should exist and they should have this speed. But this speed just so happens to be equal to the speed of light, which we've separately measured. So what does this indicate? Well, it seems pretty clear that these electromagnetic waves that we predicted just by looking at Maxwell's equations and the interaction of changing electric and changing magnetic fields must actually be light, which travels at the speed of light. And this is now understood today as providing the description of what light is. It is a self-sustaining, self-propagating combination of electric fields and magnetic fields. The electric field oscillates oriented in one direction, which we might call the x direction. The magnetic fields oscillate perpendicular to that in what we might call the y direction. Then the wave itself will travel in the z direction. Of course, this is just how we've set up our axes. We could set it up differently, but the point is that there'll be three perpendicular directions: the direction of oscillation of electric field, direction of oscillation of magnetic field, and then the direction of propagation of the wave itself. So they're all perpendicular to each other, and that again arises from Maxwell's equations, the fact that the electric and magnetic fields exist perpendicularly to each other. Now, you might be wondering, how can I have a wave that exists in a vacuum? Like, what's waving then? I understand a wave in water, the water molecules are moving, but what is waving in a vacuum? I may have addressed this question in previous episodes, I can't quite remember, but I'll discuss it briefly here again because it's very relevant to understanding the concept of electromagnetic radiation. So the point is that electromagnetic radiation is fundamentally energy. There's no material substance to it. It can, of course, travel through matter. So electromagnetic radiation, or light, can travel through glass, and in fact it can travel through any substance. It depends on the frequency of the wave, which we'll get to. So it can travel through wood, metal, and whatever else, again depending on frequency. But it's not the same thing as the substance that it travels through. It is really just an oscillating pattern of energy that has certain characteristics. So when we consider the question, though, what is waving, nothing physical has to exist in order for electromagnetic waves to exist, because they can exist in a vacuum, right? They can propagate through a vacuum. The oscillation of one part of the field, say the electric field, gives rise directly to the oscillation of the other part of the field, the magnetic field, and so which in turn gives rise to the electric field again, which in turn gives rise to the magnetic field again, and so they oscillate, sustaining each other, all the while moving in a particular direction. If we're asking the question, well, but what is oscillating? Really the only answer is the electric and magnetic fields. And if you recall, when I describe electric and magnetic fields, or just the concept of fields more generally, really the idea of a field is that it is an abstract concept of some sort of, we can think of it as a membrane, if you like, that fills all of space and time, and each point in space and time can be described by the value of that field in terms of a number and the direction. So, these are vector fields, so they have a number and a magnitude associated with them, which corresponds to the force that a charged particle would experience if placed at that location, or in the case of a magnetic field, that a magnetic dipole would rotate if placed in that location. Really, this is an abstract concept. We can say that these fields exist throughout all of space and time, and that's what we typically do, and it's the field itself that oscillates. It's not a physical substance that exists in space, it's just the field itself. And we can dive into this in a bit more depth if we talk in the context of quantum field theory, which I did in episode 85. And I'd recommend looking at that if you want a bit more discussion on what is this thing called a field, and how can you have a field without any material substance existing in it. But I guess at the end of the day, you just have to accept that the universe is that way, that space-time is such that there are these fields that exist everywhere that can have particular values, and when you have a self-propagating wave through it, then that's an electromagnetic wave. Well, with respect to the electric and magnetic fields, there are other fields that exist as well, like the gravitational field. Anyway, so that's all I'll say on that. But just, it's very important to remember that we're talking about values of the field that self-propagate. So, if you have one region of the electromagnetic field and that's changing, then that gives rise to a magnetic field, which gives rise to an electric field, and so forth. That's what I mean by self-propagating, that they move through space. That's what we're talking about here. The speed of light only applies to electromagnetic waves traveling in a vacuum. In any material substance, the actual speed that these electromagnetic waves travel will be less than that. It's reduced by the presence of matter there that essentially retards the rate of change of the electromagnetic and magnetic fields. But the electromagnetic field can still propagate through most substances. Now, as I mentioned before, because it's an oscillation, an electromagnetic wave has a particular wavelength and frequency, both of which are related to the speed. So, for example, the frequency is just the speed divided by the wavelength. The wavelength is the distance between the distance across one whole oscillation of the wave, and the frequency is the time that one whole oscillation takes. Now, in the case of an electromagnetic wave, the frequency is directly related to the energy, so they're directly proportional to each other. So high frequency means high energy. Because wavelength is inversely proportional to frequency, because if a wave is oscillating very quickly, that means that the wavelengths have to be very short, right? If you think about it, if for the oscillation to occur quickly, it can't sort of travel across a long distance of space because it would take too long to get back to its starting point, so to speak, and therefore it would have a longer frequency. So short frequency corresponds to long wavelength. So low frequency means long wavelength, means low energy. High frequency means short wavelength, which means large energy. There's no particular intrinsic limit to the wavelength that a photon can have. It could be really as small as you like, or as big as the whole universe. Obviously, if you make it small enough, then the energies will start to get so large and the distance is so small that you'll start to encounter sort of quantum effects that we can't describe using our current theory. And likewise, I suppose if you make it big enough, then the wave will become so large that it couldn't have communicated through itself over the lifespan of the whole universe, and then it becomes sort of questionable how it could be the same wave. So really, its lengths are bounded by the limits of our physical theories, but fundamentally there's no real limit, so it can be as long or short as you like. Just bearing in mind that the shorter the wavelength, the higher the frequency, the higher the energy. This variation in the possible frequencies and wavelengths gives rise to what's called the electromagnetic spectrum. The electromagnetic spectrum simply describes the range of possible frequencies or wavelengths of photons or electromagnetic waves. I'll talk about how those relate to photons in a minute, but the electromagnetic spectrum just describes the range of possible different frequencies and some of the properties of electromagnetic waves that exist in those frequencies or wavelengths. So I'll just talk through a few of the main regions of the spectrum now. Remember, there's no real limits to the edges of the spectrum. We just normally talk about sort of the main regions that we're interested in, or that are relevant to us as humans and that we can measure readily. So, at the very far right end of the spectrum, so we'll start at very low frequency, very long wavelength. So this is often written at the right-hand side of the spectrum. These are called radio waves and microwaves. Radios have the longest wavelength, radio waves have the longest wavelength, and microwaves are not quite as long, but still pretty long. So these include wavelengths from many kilometers, even many hundreds of thousands of kilometers, down to around about a meter, I think, is the edge of the radio waves, and microwaves go down to a millimeter or something like that. As the name indicates, they're used for radio transmissions. I'll talk a little bit more about that later, how that works. At these frequencies, electromagnetic radiation has fairly low energy, so the radiation isn't particularly dangerous. It doesn't have any ability to ionize matter or anything like that, but it does have the ability to induce bulk movement of charges, like electric currents, by interacting with matter over a collection of many molecules spread out over a large area. So it can't excite electrons in single atoms because it doesn't have the energy, but it can move sort of charges over a bulk portion of a substance. So that's why we can use it to transmit energy using antennae for radio transmissions, because we don't need to interact with single molecules or single electrons for that technology. We just need sort of gross electric currents or voltages to be generated, and so we can absorb the radio wave through using an antenna, which is quite large and doesn't have to be microscopic or anything to interact with the wave. Microwaves are used in microwave ovens, hence the name. Micro meaning sort of small because they're smaller than radio waves, although they're still reasonably large by comparison to the other waves. Next down in the spectrum, reducing the wavelength still further, is what's called infrared. Infrared waves extend from around 1 millimeter, which is about as small as you can get with microwaves, down to the edge of the visible spectrum, about 700 nanometers. Infrared radiation typically interacts with single molecules, and so it can change the vibration energy of atoms and of single chemical bonds. So because of that, it is absorbed by a wide range of different substances, because you're not just acting on the bulk matter like radio waves do, but you can act on individual molecules within that substance and chemical bonds. And this means that infrared radiation can directly interact with, as I said, the vibration levels of those molecules, and therefore it's directly related to heat. If you recall, I don't remember which episode, but I've talked about black bodies before. A black body is an abstract object which absorbs all of the incident light and therefore doesn't reflect any light. As such, the only light that is emitted by a black body is that produced by the temperature, the intrinsic temperature of that body itself, and there is a well-defined spectrum dependent on the temperature of the object or of the body that describes how much light will be emitted at different wavelengths or different frequencies. Now, the point is that infrared radiation is the most common, or the peak type of electromagnetic radiation that is emitted by objects at sort of what we would regard as ordinary temperatures. So, like at room temperature. So people and other objects emit energy mostly in the infrared region of the spectrum, of the EM spectrum. Now that doesn't mean humans are black bodies, right? Because we also reflect some of the light that's incident on us, because you can see us, right? So when you see people, you're not seeing the light that they emit in the infrared, because that's not visible to human eyes. You see the light that reflects from them. The point, though, is that the fact that electromagnetic radiation in the infrared part of the spectrum is able to interact with the vibration levels of energy levels of molecules in water and carbohydrates and other of the sorts of molecules that make up people, is directly related to the fact that infrared is the region of the spectrum that humans and other animals mostly emit light as a result of our intrinsic temperature. This is why thermal imaging techniques work, because they don't detect visible light, they detect infrared, mostly infrared light, and that is emitted by objects like humans, which we emit more of this than objects like a table or a chair, because those objects are not, they're generally are at a cooler temperature, because humans are warm-blooded animals, and so we have a higher temperature than our environment, right? The point is that infrared vision works by tapping into the energy or the electromagnetic radiation that is actually being emitted by humans, rather than the light that's reflected off the surface of humans and other animals, which is what we see in visible light. So, and that directly relates to the energy that those particular infrared photons have, and the types of molecules and energy levels that they can interact with. It's vibrational energy levels that give rise to, that are related to temperature, and therefore if you can interact with the vibrational energy levels, then you're going to be related to temperature. And it's infrared light that reacts with those vibrational levels in humans. Of course, for other objects it's different, like in terms of the sun, which is obviously much higher temperature than humans, thousands of degrees at the surface rather than like 37 degrees as in humans. It will have a spectrum which peaks actually in the visible region of the spectrum. So, in a sense, the way we see the sun is the way that thermal vision sees us. It sees the light that is emitted because of the temperature of that object, not light that's reflected off the surface. Of course, it's a bit more complicated than that because we're seeing the surface of the sun and there's scattering that occurs there. Plus, we see it through the atmosphere and there's more scattering. But anyway, hopefully you see the point, that there are different ways of seeing an object, either through the light that's emitted by the because of the temperature of that object, or by a light that's scattered off the surface, reflected off the surface of that object. Alright, let's move along. Let's move on to visible light, which is obviously the most well-known part of the spectrum. It's also the narrowest part of the spectrum. It's only a tiny, tiny sliver between about 700 and about 400 nanometers. So whereas the other regions of the spectrum encompass usually several orders of magnitude, like radio waves of from 1 meter to hundreds of thousands of kilometers, visible is only a very tiny proportion, not even a whole order of magnitude, just from 400 to 700 roughly nanometers, and it's defined by the region that we can see with our eyes. Now, why is this relevant? Well, it's because, as I mentioned, the visible region of the spectrum is the area that the sun emits most of its energy in. Now, it's not like that the sun was just really convenient for us in deciding that, I'll just emit, I'll set myself up so that I emit my energy mostly in the region you can see. Obviously, it works the other way around, right? We evolved, or our ancestors evolved, to be most sensitive to the types of electromagnetic radiation that the sun emits most of its energy in, because obviously that's most useful. In fact, the sun also emits quite a lot of energy in other regions as well, but again, it emits most of its energy. The peak of its black body spectrum is in the visible region of the spectrum, and so that's where our vision has been honed by evolution. Obviously, we see different colors. These different colors correspond to different frequencies of light. I think most people know that. So So violet is at the shorter wavelength, higher energy end of the spectrum, then going through blue, green, yellow, orange up to red at the longer wavelength, lower energy end of the spectrum. So think of blue as high energy and red as low energy, which is interesting because I think that that's probably the opposite of our, at least in my mind, cultural connotations, where red is sort of more high energy associated with like warfare, blood, fire, that sort of thing, whereas blue is more sort of tranquil, quiet, peaceful. Maybe you think differently. But anyways, visible light is, like infrared, able to interact with molecules, although it's a bit higher energy, so it's able to be absorbed by certain molecules such as rhodopsin in the retina of a human eye, which allows us to see visible light. Have a look back at the episodes I've done on human vision for more detail on that. Moving on now to ultraviolet radiation, which encompasses electromagnetic radiation of wavelengths from a maximum of 400 nanometers down to about 10 nanometers. So again, fairly narrow range of the spectrum, wider than visible though. So this is even higher energy than the visible spectrum, and photons in this range carry enough energy to make permanent chemical changes to molecules. So they're higher energy again, and so can do more chemical damage. So that's why ultraviolet radiation is dangerous. It can particularly induce permanent chemical changes in DNA mutations. That's why we need to apply sunscreen, because sunlight also contains, although it peaks in the visible spectrum, it contains quite a bit of ultraviolet light as well, and more than enough to cause damage if you expose yourself for too long in the sun. The higher energy of ultraviolet radiation is essentially what allows this. Moving on then to X-rays, which have wavelengths of about from 10 nanometers to 1/100th of a nanometer, and gamma rays, which are smaller than X-rays. So these are the highest energy types of light. These X-rays and gamma rays have enough energy to directly interact with electrons surrounding atoms, and particularly to ionize atoms. So this is ionizing radiation. I think, some forms of high energy ultraviolet radiation can cause ionization as well, but mainly X-rays and gamma rays are the ionizing radiation. So this means they have high enough energy to interact directly with the electron and the energy level surrounding an atom. Basically, you can think of it as the smaller the object is that you want to directly interact with, the lower the energy that you need to interact with it. So bulk matter is big, so it's less energy than molecules, which in turn is less energy than smaller molecules, which is less energy than individual atoms and electrons in those atoms. So X-rays and gamma rays are more dangerous again because they can directly and to a very substantial degree disrupt bonds and the complex chemical arrangements of bonding in organic molecules that make up organic tissue, right? So they can cause mutations, cancer, and all sorts of other nasty things, which again I think I've talked about in past episodes, so I won't go into too much detail here. Thankfully for us, many of the most dangerous forms of gamma, X-rays, and ultraviolet radiation are blocked by the upper atmosphere. In part, this is because they are ionizing radiation, and therefore they are deflected by electric and magnetic fields, which the Earth produces as part of the magnetosphere. So they're generally deflected away from the Earth. If not, then I don't think humans will be able to survive on the surface of the Earth, because we'd be bombarded by high levels of this of these, both solar and also cosmic radiation, so radiation of an extrasolar origin, and we would have too many mutations and other negative consequences on our biochemistry to be able to live. The Earth's atmosphere also blocks out long-wave radio waves and most of the infrared spectrum. So the Earth's atmosphere is only transparent to visible spectrum, some parts of the ultraviolet and infrared spectrum, and shorter wavelength radio waves. So that's one of the reasons why radio astronomy is so popular, because apart from visible and some parts of the infrared, we can't really see much of the radiation that's generated by stars or other extrasolar objects apart from radio waves, because it's blocked by the Earth's atmosphere. Of course, you can put satellites in orbit which can look at anything, but that's a lot more expensive. So those big radio dishes, they're part of the radio astronomy effort, which is looking at these wavelengths of light that the Earth's atmosphere is transparent to. Okay, so we've talked about the different regions of the electromagnetic spectrum and some of the properties of the radiation here. The basic idea is that longer wavelengths are less harmful to humans because they don't have the energy to disrupt our biochemistry, and shorter wavelengths have higher energy and are more and more dangerous. Let's talk a little bit about some applications of electromagnetic radiation, apart from, allowing us to see, right? So one is radio and TV. So radio waves get their name from the fact that they're used in radio transmissions and other types of broadcasts like television. The way this works is by use of two overlapping waves. So there's something called a carrier wave and an input or a signal wave or a modulating wave. And the idea is that these are combined, so you overlap them and produce a resultant wave, which is what you actually beam over the air. There are two main types of this that are called amplitude modulation and frequency modulation, or AM and FM, corresponding to the two main waves that radio can be sent out. These days there's also digital modulation, which is a bit different again. But the basic idea is, say, let's take amplitude modulation. You have an input signal which encodes the key information you want, and then a carrier signal. The way that you encode the input signal into the carrier signal is by varying the amplitude of the carrier wave. So the carrier wave is just like a sine wave. It just has a constant frequency and constant amplitude. And, if you were to listen to it, it'd be pretty boring because it would just, be a constant sort of sound, a single constant pitch, not very interesting. But the way you make it into be aiming to encode actually interesting information is by modulating the amplitude of the wave, so it goes up and down. And by modulating that, you can encode a signal, which can then be decoded by the recipient. I'll talk about antenna and how these actually transmitted in a moment, but once you receive the modulated result, the wave that's actually transmitted, you extract the carrier wave and are able to read the modulating wave, which directly encodes the signal that you want. In frequency modulation, it works the same way, except instead of altering the amplitude of the carrier wave, you alter its frequency, and so its frequency goes up and down. Remember, a carrier wave, the electromagnetic field itself is increasing and decreasing in accordance with, a wave, but the point is that you, instead of just having one fixed frequency, you modulate the frequency. And it's in frequency modulation, whereas in amplitude modulation, you modulate the amplitude of these oscillations. So the oscillations keep going, but their amplitude varies. So these are two ways of transmitting information over the radio waves. In digital modulation, the carrier wave is essentially the same, but you have an input which is a series of zeros or ones instead of an analog, continuously varying input wave like you have in AM and FM methods. But fundamentally, it's the same thing. The modulated result wave is the one that's actually transmitted directly. You subtract the carrier wave from that and are able to read off the input wave, which carries the actual information that you're interested in. Okay, so let me talk now about electromagnetic radiation itself. I've kind of been, in a sense, talking about this the whole episode, but in electromagnetism, radiation refers to something quite specific. It refers to energy that's transmitted, or variations in the electromagnetic field that is transmitted, or it can be transmitted a long distance, what's called the far field. So there's this distinction between near field and far field in study of electromagnetic waves. And basically it just means like close to source and far away from the source. The term is somewhat vague, but usually close to source is within maybe one or two wavelengths, so it obviously depends on the wavelength of light EM radiation that we're concerned about. 1 to 2 wavelengths is the near field, and more than 2 wavelengths or so is the far field, so that's far away. Now why do we make this distinction? Well, the reason we make it is because there are different effects that dominate in the near field and the far field, and this all comes down to mathematics. When we have a dipole that's oscillating, that's changing in orientation from one to the other, that will generate an electromagnetic field, right? Any acceleration of charge generates an electromagnetic field, which then can propagate throughout space. But the effects that are generated, so that the changing patterns of electric and magnetic fields that are generated by a dipole oscillation, or an oscillation of charge more generally, are quite complicated. So it's not just like one thing, there are many effects that will exist. The key point, though, is that some of those effects die off very quickly and therefore are only observed in the near field. That is, they're only observed very close to the source. Some of these effects, some of these variations in the electromagnetic field, don't die off very quickly and in fact can be propagated to infinitely far, to arbitrarily long distances. These are the far field effects. So all of these effects are produced by the same source, and they all exist in the near field. It's just that the near field effects dominate, but then they gradually die out. So they start off big but die out very quickly, whereas the far field effects start off smaller but don't die out nearly as quickly, and therefore in the far field limit, or a longer distance away from the source, they will come to dominate over the near field effects, which have all long died out. Only the far field effects are examples of what we think of as true radiation, because they can be transmitted for long distances. These near field effects, although they're still electromagnetic waves, but they don't get to be classified as true radiation because they can't be transmitted by long distances. In a quantum view, if you're more comfortable there, only the far field effects are manifestations of real photons, whereas near field effects are due to a mixture of real and virtual photons. Have a look at my quantum episodes if you want to know more about virtual photons. At this point, I should explain, I did promise that I would explain what is a photon, how it fits into this picture, because we think of a photon, at least the way I think of a photon, as like a little ball, which is a single particle, a single encapsulation of electromagnetic energy, and I can shoot photons one at a time, and they can be absorbed one at a time, and each carries a certain amount of energy. And that's all true as far as it goes. They're not really a ball, they're a point-like particle, but you can think of them as a ball. That's a helpful way to depict them. And they are discrete, so you can't have half a photon. It's 1, 2, and so forth. And you absorb them and emit them in single units. You can't emit part of a photon and wait a while and then emit the other part. That doesn't make any sense. Right? So far, so good. But how does that fit with the electromagnetic waves that we've been talking about, which are a continuous variation in electromagnetic fields? There's no single unit there. Like, where does the photon appear in this? The best way that I can explain this is in terms of the uncertainty principle. Because remember, fundamentally a photon is a quantum object. It doesn't really fit into the classical electromagnetism that I've mostly been describing so far. So everything that I've been describing so far that didn't say anything about photons is all 19th century classical physics. You don't actually have to incorporate photons to get any of this stuff. Photons are only really incorporated into this later when certain effects were observed, like the photoelectric effect, that could not be explained by classical electromagnetic theory, and therefore basically Einstein and Bohr and others working at the time had to develop a new theory that could incorporate these effects, and I talk about this in various quantum episodes. I think the history of the atom, which is episode 8, is the first one where I start talking about this stuff, so go back there if you're interested in this story here. The point here, though, is to understand most of the behavior of electromagnetic radiation, you don't really need to talk about quantum mechanics to understand it on a classical level, right? To make radios and do all this stuff. However, the issue is that a lot of people who have some science knowledge know about photons, and they often think of light as emission and absorption of photons. And if they've done a bit of quantum mechanics, they know about, energy levels of the electron and emitting and absorbing a photon and all this sort of stuff. So, this is when I was studying this. I was like, but how does a photon fit into this? I don't see room for a photon here. It's just, continuously varying waves. There's no discrete packets here. What's going on? And indeed, this is a valid question. This is what, at the turn of the 20th century, people were debating about. Like, but classical electromagnetism doesn't need photons. Why do you need these discrete packets thing? Well, what's this nonsense about? And trying to fit these two together. This is why we talk about duality, about something being a particle and a wave at the same time, even though we think that those are kind of different things. Well, here's a short version of the answer here. It's not the whole story, but it's enough for our purposes. One way to think about this is that a photon is a sort of a smearing of electromagnetic waves across a number of different wavelengths. So if I were to take an electromagnetic wave of one exact frequency, it'll be like a sine wave. It'll go up and down from negative infinity to positive infinity, right? Now, that is not a photon, clearly, because it exists throughout, all of space. There's no spatial limit to it. It just exists everywhere. In order to provide a spatial limitation to that, what I need to do is smear out the frequency. So it doesn't have a frequency of 10. It has a range of frequencies from 9.5 to 10.5. Now, I'm just choosing arbitrary numbers here to illustrate the point, right? Now, it turns out when you do that, you introduce constructive and destructive interference in such a way that you actually localize the regions where the particle actually exists. So some regions, the electric field and magnetic field will be essentially zero, whereas other regions it will be much larger. You can really only see this in a diagram, so you just have to believe me if you're just listening to audio, right? But you can see diagrams of this, and I'll hopefully put some up that you can look at. But the basic idea is the more I smear out the frequency of my photon, the more spatially localized I can make it. And there are other effects as well, like there's always a finite time that photons exist for, and so you can't sort of talk about them spatially existing over an arbitrary fraction of the universe. There's a time when they're emitted and a time when they're absorbed, so we have to sort of restrict our attention to these regions. So in other words, there's always boundary conditions on the existence of a photon which put extra constraints on its behavior. But anyway, the point is, you can think of a photon as like a smearing of electromagnetic waves of a particular range of frequencies, which produces something called a wave packet, whereby it's not one single wave with one single frequency, it's a bunch of frequencies sort of that travel together as kind of like a packet. When it's emitted and when it's absorbed, it will have a distinct frequency, but you don't necessarily know exactly what it will be. This is related to uncertainty, right? There'll be some uncertainty in the time of existence of the photon, which will be related to its uncertainty in energy, and that in turn relates to uncertainty in its frequency. And these uncertainties are fairly small for most of these, but they're enough to sort of spatially localize the particle or the wave packet, if you prefer, so that it can be absorbed and emitted as a single sort of discrete unit. that doesn't do justice to exactly what's happening here, but it's a first glimpse into trying to understand how photons fit into this picture. I mean, the more honest answer is that they kind of don't, because this is all classical electromagnetism, and you really have to go to quantum field theory in order to fully integrate electromagnetism and the quantum view of matter. And you can have a look at my Introduction to Quantum Field Theory episode 85 if you're interested in that. Yes, the most honest answer is photons don't really fit into this picture. The slightly less honest but more informative answer is that they do. You can think of it as a wave packet of smearing out of frequencies, which spatially localizes the photon to some degree. But in both cases, have a look at quantum field theory if you want the full answer here, because this isn't the full answer, it's only the first approximation. Okay, enough on photons. Let's go back to talking about the near field and the far field. Remember, what I was saying is that the far field can be thought of as the region where actual photons are being transmitted, where light is being radiated long distances. And it's because in the far field, the radiation only decays proportional to 1 over r, where r is the distance from the source. So it decays fairly slowly, and these fields can therefore propagate out long distances. Whereas in the near field region, the fields die out at 1 over r squared or 1 over r cubed, or even faster for higher effects. And therefore, they just aren't able to propagate as far because the effects go to 0 very quickly. And only the distant part of the field, the far part of the field, is called electromagnetic radiation. That's the stuff that, antennae emit and so forth. This is important because there are different behaviors that are exhibited by any substance that can interact with electromagnetic waves, depending on whether you're looking at the near field or the far field limit. So there are two different types of diffraction. Remember, diffraction is when radiation passes through a small slit that's small compared to the wavelength of the radiation. So near field diffraction is what you observe if you look at the results from passing a wave through a small slit. But if you're sort of imagining looking at the results very close to the slit, that's called Fresnel diffraction. Whereas if you look much further away, that's called Fraunhofer diffraction. That's far field diffraction. The diffraction pattern that you observe looks different, and the mathematics are quite different as well. You sort of make different approximations when r is big compared to when r is small, when you're close compared to when you're far away. And this is important when we're designing electromagnetically sensitive devices like wires and transistors and other things like that, because you have to look at what the effects are going to be of light interacting with them near to the object and then farther away from the object and so forth. So that's only a sort of a brief gesture towards that whole rich field, but it's important to understand the near field and far field distinction. In talking about propagation of waves, I also want to mention very briefly how antennae work. Fundamentally, an antenna is just a wire with a resistor in it that is able to essentially resonate at the frequency of the wave, the electromagnetic wave that it's able to absorb and re-emit. So, that's why you will get a better signal if you extend the antenna on your radio, because radio waves are reasonably long, and therefore you need an antenna that is similar in size to, physically similar in dimensions to, the length of the waves that it's trying to pick up. So that's why radio antenna can't really be very small. I mean, using clever techniques they can make them smaller, but you're always going to suffer in quality to some degree. So they have to be reasonably large, and really all they're doing fundamentally is when the electric field, that oscillation comes in, so the antenna's picking up a signal, the charges in the electric, essentially rod, which represents the antennae, the positive charges move one way in response to the field, the negative charges move the other way. That generates a voltage difference, a potential difference, which then gives rise to a flow of current to offset that. Then as the wave comes in, because you've got the one oscillation, so the electric field's pointed one way, which drives the current one way, and then the next part of the as the peak passes through, charges falls one way, then as the trough of the waves comes through and is picked up by the antenna, the charge is pushed back the other way, and then it's pushed back in the first direction and then in the later direction, and so on. The variations in how that works, in the pushing of charge one way or the other, can be picked up by whatever circuit the antenna is connected to and used to, say, generate a sound. So, you have a speaker that's connected up to the antenna. Essentially, the antenna is driving a current in the circuit that it's connected to, which varies in frequency and amplitude, and you connect that up to a speaker using the appropriate circuitry, and it's able to generate sound whose frequency and volume varies in accordance with the electrical signal that you're picking up, and therefore you get a sound which we interpret as, which we interpret as someone speaking or singing or whatever. The actual quality of the sound is quite different, obviously, but the point is that as long as the speaker's good enough that we can pick it up and our hearing system and smart brain can do the rest, we can understand what's happening there. It's obviously, you can tell the difference between a radio broadcast and someone speaking to you, so it's not like all of that information is being encoded and transmitted, but enough of it is so that you can understand it most of the time. So this is essentially how radios work in a very simplified way. You've just got the antenna, which is resonating in accordance with the field that it picks up, and that drives current or voltage potential differences in a circuit that is then connected to a speaker. You can also have antennae which pick up a signal, and then the circuit that's connected to a circuit which amplifies that signal and then sends it out again, so it re-resonates it. So that's how, by boosting the signal periodically, you can send signals, all around the globe, essentially, if it's just periodically boosted in this way. This is one of the reasons why radio waves are used for this, because they can travel such long distances because of their long wavelength and the fact that most objects are transparent to them, so they can pass through buildings and so forth. I mean, they can be obstructed, but for the most part, they'll travel through most objects. So you don't necessarily need an unimpeded line of sight from the transmitter to get a good signal, although that often helps. Radio waves can also be scattered off the upper atmosphere because of particular effects that help. So you can actually get sort of scattering of waves across the horizon, even from sources that you can't observe. So there's a lot of other complexity in there that we won't get into here. When you tune your radio, although I guess manually changing the dial is something that isn't really done anymore, but hopefully you know what I'm talking about. Really what you're doing, I mean, it's still the same in a digital radio, it's just it's not as direct, but what you're doing is you're changing the resonant frequency of the circuit and antenna system so that you're kind of looking for a different frequency of EM radiation that you'll pick up. And of course, if there's very little signal there, then you'll just get static, you'll just get noise. But the point is that different carrier frequencies, remember I talked about the carrier and the signal frequency, different carrier frequencies will have different frequencies, obviously, that they're at, and if in order to pick up that carrier frequency, you have to tune your radio to the corresponding frequency so that it will resonate with that frequency. Different regions of the electromagnetic spectrum are reserved for different purposes, so you can't just go and broadcast on whatever frequency you like. There's particular regions that are reserved for ham radio users, and there's particular regions that are observed for commercial stations. You can buy a region of the spectrum, and some are reserved for military uses and so on, and there's a whole lot of regulation around this, which is quite interesting. The final thing that I wanted to finish out this episode with is just a very short look at microwave ovens, because these use microwaves, as you probably would have guessed, to heat food. And they're a very different way of cooking than traditional ovens. People would usually just call them microwaves, at least where I'm from, everyone would just say microwave, but originally they were called microwave ovens. And the idea here is you basically just generate a fairly high energy microwave, and that bounces around inside your little box. What then happens there is that the food is warmed by absorbing the energy from the microwaves in a process called dielectric heating. So essentially what happens is that, if you recall, I said that microwaves have about the right energy to excite vibrations in molecules, in particular water molecules. So water molecules are very useful because they are dipoles, because there's an oxygen and two hydrogens, and the oxygen is highly electronegative, so it kind of pulls the electrons closer to it, and so has a partial negative charge. The hydrogens aren't able to hold onto the electrons as much, so they have a partial positive charge, producing what's called a dipole. So each water molecule is kind of like a little electric dipole with a positive end and a negative end. If you place these in an electric field, they tend to align in accordance with the field. Positive end will point in the direction of the field, and the negative end, in the opposite direction. And if you change the direction of the field, then they'll flip sort of backwards and forwards depending on the direction of the field. Now, as they flip backwards and forwards, if you flip the field's polarization or orientation very quickly, the molecules will flip backwards and forwards, and in the process they will kind of interact, bump into each other, slip past each other, and so on. And there will be a kind of friction between the molecules, kind of bumping into each other, dispersing energy as heat. So effectively you're tapping into the molecular rotations and vibrations of particularly the water molecules, and that energy, some of that energy is released as heat energy, which obviously heats up the food. So it's not as effective in carbohydrates, which are mostly non-polar, big long chains of carbons, but it will still heat those to some extent. It mostly has its effect by warming up water. So foods with high water content will generally be microwaved more efficiently than foods with a low water content. Of course, you have to consider other factors like water has a very high specific heat capacity, so although it's heated effectively by microwaves, you also have to put in a lot of energy to just heat it up in the first place because it needs so much, and so there's that effect as well. Basically what happens is that you heat up the water molecules in particular, and then that heat is diffused just, through one molecule heating another, is diffused throughout the food. And that heats it up without actually charring it or cooking it in a more traditional oven. A more traditional oven actually, the food undergoes a chemical reaction when it reaches a certain energy. Basically, you remember a chemical reaction, the idea is you're moving the reactants across an energy barrier into a more stable state. But often that energy barrier is fairly high, so it requires you to put in a lot of energy. Conventional ovens are able to put in enough energy to push you over the energy barrier and alter the food in some way, often effectively by burning it to some extent, or like burning it in a tasty way, I suppose. Although there are a lot of other complicated effects that occur as well. Maybe I'll do a whole episode at some point on like science of cooking or something. That'd be interesting. But anyway, microwave ovens rarely do that. They pretty much just increase the kinetic energy of the molecules in the food, which means that it won't actually cook anything as such, like in terms of the food undergoing a chemical reaction which changes it. It will just warm it up. So that's why microwave ovens are basically just used for warming food up and not usually for cooking it as such. It's just all about the chemistry of what's actually happening. In fact, there aren't any, again, usually, there's not any actual chemical reaction that occurs in a microwave oven, or shouldn't occur. Like, you're normally not trying to get one. It's actually just a transfer of the dipoles in the water flipping backwards and forwards, and that energy being dispersed as kinetic energy, which then heats the food up. So it's actually fundamentally quite a different process to when you put the food in an actual oven or a toaster or something. Okay, so that concludes this episode. Hopefully you enjoyed it and learned something about electromagnetic radiation. If you have some comments or suggestions or other feedback, please feel free to email me. My address is fods12@gmail.com. That's fods12@gmail.com. You can also jump on Facebook and find the Science of Everything Facebook page to get information about upcoming episodes and visuals and other things like that. Also, I have an announcement. I have set up a Patreon account for the podcast. So if you're interested in making a donation, and I emphasize these are only donations, you're not buying anything, there's no extra content there, because I have a pledge that all of the content from the podcast will be free for everyone. But if you enjoy the show, find it valuable, and would like to contribute to the cost of maintaining the website, and also help contribute to the cost of time and effort and other things put into the research, feel free to make a donation there. I've got a few different levels of subscriptions that you can subscribe to. All of them are dependent only on episode release, so the more episodes I release, the more donation you will make. But if I don't release episodes for a while, you won't be charged at all. So it's purely on content. It's purely related to content production and not amount of time. So if you would like to contribute, please check that out. You can just go to Patreon and search for the Science of Everything podcast, and hopefully you should be able to find it there. So once again, thank you very much for listening, and I will talk to you next time.